Hello, in this video we'll be working through Unit 7 homework problems 21 through 30. For number 21, we're asked to find the area of the region bounded by y equals x squared and y equals x cubed. So we're given the graphs and we're asked to do this two different ways, one using a vertical cross-section and once using a horizontal cross-section. But the area of the region won't change, so we should get the same answer either way we set this up. In part A, we're going to use a vertical cross-section. So that means my Riemann sum is going to have vertical rectangles. I'm just going to draw one of these rectangles for my Riemann sum as a reference to help me set up the problem. And I know that if this is a vertical rectangle, then the width of the rectangle is dx. So my integral is going to be a dx problem. And if it's a dx problem, then my lower limit of integration and my upper limit of integration are going to be x values. So our points of intersection are 0, 0, and 1, 1. So I'm going to integrate from x equals 0 to x equals 1. And I'm going to integrate the height of this rectangle. If I go back to my reference rectangle, the top of the rectangle is touching the yellow graph and the bottom is touching the blue graph. So I guess I need to figure out which equation is which. The equation on top is y equals x squared. The equation on the bottom, y equals x cubed. Since we're working on the interval between 0 and 1, for values between 0 and 1, x squared is larger than x cubed. So top minus bottom will give me the vertical distance between the top and bottom of my rectangle. In other words, it'll give me the height of my rectangle. So that will be x squared minus x cubed. That's the height of my rectangle, and then the width of my rectangle is the dx. We multiply the height times the width, we get the area of the rectangle, and the integral sums up all of these possible rectangles that we can draw as the width approaches 0. We're going to go ahead and do this, evaluate this integral by hand. So we'll use our power rule. The antiderivative of x squared is x cubed over 3 minus, and then the antiderivative of x cubed is x to the 4th over 4. And we want to evaluate that from 0 to 1. So we get 1/3 minus 1/4 minus 0 minus 0. 1/3 minus 1/4, if we get a common denominator of 12, is 4 over 12 minus 3 over 12, or 1 over 12. So that's the area of my region. Now let's try this same problem again, but we're going to use a horizontal cross-section. So when I have a horizontal cross-section, the width of the rectangle, I'm thinking of the rectangle being turned on its side. So this is dy, that dimension there is dy. And then the height, again, if we're thinking of it turned on its side, or the length, the horizontal distance between one end of the rectangle and the other, is going to be the right side minus the left side. So when you're finding horizontal distance, you do right minus left. If you want vertical distance, you do top minus bottom. So we have to figure out which equation is on the right, which equation is on the left. And we already know from the last problem, part A, that this, on the right-hand side, we have the graph of y equals x cubed. But since this is a dy problem, when we set up our integral, we're going to have dy at the end. And so we can't use x cubed. We have to solve this equation for x so that it's written in terms of y. So if y equals x cubed, then x equals the cube root of y. And then my equation on the left is y equals x squared. But again, I can't put x squared into a dy problem. I need to solve this equation for x. So if y equals x squared, then x equals plus or minus the square root of y. But I'm working with the right half of the parabola. That's positive square root y. If I were working with the left half of the parabola, it would be negative square root y. So we want now to integrate right minus left, which is cube root of y minus square root of y. And we're integrating from a y value of 0 all the way up to a y value of 1. Again, this is something that we can evaluate by hand, going from y equals 0 to y equals 1. I'm going to rewrite the cube root of y as y to the power 1/3, and then the square root of y as y to the power 1/2. And we can use our power rule for integration. So we're going to get y to the 4/3 times 3/4 minus y to the 3/2 times 2/3, and we want to evaluate from 0 to 1. When we substitute 1 in for y, we get 3/4 minus 2/3. When we substitute 0 in for y, we get 0 minus 0. So now this is 3/4 minus 2/3, and if we use the common denominator of 12, that's 9 minus 8 over 12, which is 1 over 12. So the area of the region, again, is 1 over 12. Number 22, find the area of the region bounded by y equals square root of x and y equals 1/4 x. So this time let's start by identifying which is the top function and then which is the bottom function. So for a vertical cross-section problem, our top function is y equals square root of x. And our bottom function, y equals 1/4 x. Our points of intersection are 0, 0, and I'm just going to kind of guess that looks like it's 16, 4, and I can verify that by putting 16 in for x and 4 in for y and seeing if that works for that equation. And yes, 4 is the square root of 16, so it works for that equation. And then over here in this equation is 4 equal to 1/4 times 16. Yes, it is. Which tells me that my point of intersection here is 16, 4. And like I said, the other one is 0, 0. So for a vertical cross section, we draw a vertical reference rectangle. That makes this a dx problem. When we set up our integral then, we need x coordinates for our lower and upper limits of integration. So we're going to use the x coordinates of our points of intersection. We're going to integrate from 0 to 16. The width of my rectangle is dx. The height of my rectangle I'm going to get by doing top minus bottom. So square root of x minus 1/4 x times dx. We can integrate this with power rule. Think of the square root of x as x to the 1/2. So we get x to the 3/2 times 2/3 minus 1/4 x squared over 2. So that becomes 1 over 8 x squared. And then we evaluate from 0 to 16. X to the 3/2 when x is 16. So 16 to the 1/2 is 4, and then we cube that and get 64. Multiplied by 2, we get 128 over 3. Minus, okay, here I have 16 squared. Well, 16 squared is the same as 8 times 2 times 16, and then I can cancel an 8. So I really just have 2 times 16, or 32. Minus, and now I sub in 0. That's just 0 minus 0. So if we use 3 as a common denominator, this is 128 minus 32 times 3 is 96. And 128 minus 96 is 32. So 32 over 3 is the area of my region. Now let's try that same problem using a horizontal cross-section. So for horizontal cross-section, I need to know what is my equation on the right. And because this is going to be a dy problem, I want my equations in the form of x equals something in terms of y. So this is the equation y equals 1/4 x. We want to solve for x, so we get x equals 4 times y. My left equation is y equals the square root of x, but if I solve that for x, I get x equals y squared. And I have the same points of intersection, of course. So since this one is a dy problem, I need y coordinates for my lower and upper limits of integration. We're going from y equals 0 all the way up to y equals 4. Right minus left, so 4y minus y squared times dy. And we can integrate this using power rule. So we get 4y squared over 2, or 2y squared, minus y cubed over 3, and evaluate from 0 to 4. So when we sub in 4, we get 2 times 16 is 32, minus 4 cubed is 64 over 3, minus, and then when we sub in the 0, we just get 0 minus 0. So 32 minus 64 thirds. If we get a common denominator there, 32 times 3 we said was 96, minus 64 over 3. 96 minus 64 is 32 over 3, so the area is 32 over 3, which is the same answer we got when we tried it the other way. Find the area of the region bounded by y equals 2 minus x squared and y equals x. So let's label our equations. We've got the yellow function y equals 2 minus x squared, and then this blue function over here is the y equals x. For a vertical cross section, we're going to draw a vertical reference rectangle, which makes this a dx problem. So I know when I set up my integral, I'm using x coordinates, and it's going to be something times dx. So my points of intersection here, it looks like it's -2, -2, and then 1, 1, but I'm going to verify that by substituting those values into both equations and just making sure that that is accurate. So -2, -2 definitely works for y equals x. 1 equals 1 works for y equals x. And then 2 minus -2 squared is 2 minus 4, or -2. So that works. 2 minus 1 squared is 1, so that works. So points of intersection, -2, 2, -2, -2, and 1, 1. We're going from x equals -2 to x equals 1. And we're going to do top minus bottom. So 2 minus x squared minus the bottom function, which is just x, times dx. So we can integrate this using power rule. 2x minus x cubed over 3 minus x squared over 2. And we're going to evaluate from -2 to 1. So at x equals 1, we get 2 minus 1/3 minus 1/2, minus at -2, we get -4 plus 8 over 3 minus 4 over 2, or just -2. Okay, so if we add up all of our whole numbers, we've got 2 plus 4 is 6, plus 2 is 8. I'm distributing the negative there. And then for our fractions, I have, let's do everything out of 6. So the -1/3 becomes -2 over 6. The -1/2 becomes -3 over 6. Then I have -8/3 is -16 over 6. So that's -21 over 6, and then 8 would be 48 out of 6. And what did I say? 19, 20, 21. So that gives us 27 over 6. And 27 over 6, if we divide top and bottom by 3, is 9 over 2. Now let's try that again using horizontal cross-section. So for horizontal cross-section, we actually run into a problem. Let me erase some of this. So we'll just remember that it was 9 over 2. And now we have some more room to work. We're going to need it. So horizontal cross-section, we kind of have a problem here because if we try and draw a reference rectangle horizontal, and I draw the rectangle down here, I have different right and left functions than if I draw the rectangle up here. So where does it change? Where does the right function change? Well, it happens right here at this point of intersection. So in order to do this using horizontal cross sections, we would have to split this up into two integrals. Remember, this point of intersection is at 1, 1. So one of our integrals could go from -2 up to 1, and then the second integral can go from 1 up to the top here, which is has a y value of 2. So, okay, that problem is easily solved. But the other problem is that in this top area between y equals 1 and y equals 2, right minus left is touching the same curve. So we can't just say it's that function minus itself, because that would mean that the length is 0, which is clearly not true. So we have to do a lot of work to get this to work. I would never ask you to do a problem like this using a horizontal cross-section. I actually wouldn't expect you to do it right now either. I'm just going to work through it to show you that it is possible. In order to do horizontal cross sections, becomes a dy problem, remember? And that means we have to write our integral in terms of y, so we have to solve our equations for x. So no big deal for this one. This was y equals x, and so x equals y. Easy. But the parabola, so it takes a little bit more work to solve that for x. Our parabola, we had y equals 2 minus x squared. So off to the side here, let's solve that for x. We've got y equals 2 minus x squared, which means x squared equals 2 minus y, and then x equals plus or minus the square root of 2 minus y. So x equals plus square root 2 minus y, that is the right half of that parabola on the right. X equals negative square root 2 minus y, that's the left half of the parabola. So in order to make these functions, we have to just consider the left and the right separately with respect to y, functions with respect to y. So the equation for the left half of this parabola is x equals negative square root 2 minus y. Then the equation for the right half, let's see if I can fit it in there, would just be x equals the square root of 2 minus y. Okay, I think we have everything labeled that we need. Here's my other point of intersection down here. So let's go ahead and set this up. We have our first integral that goes from y equals -2 up to y equals 1. And in that region, the right function is y. Remember, we rewrote our equation for x in terms of y. So my right function is just y. And then my left function is negative square root 2 minus y. So I'm doing right minus left, and that minus negative actually makes it y plus the square root of 2 minus y. So we had a double negative there. And we integrate that with respect to y. Plus, and then I have an integral that starts at y equals 1 and goes up to y equals 2. And we're going to do right minus left here. So the right side is square root 2 minus y minus the left side is negative square root 2 minus y, and then times dy. So we can simplify that a bit. Not the first one, really. We've got integral from y equals negative 2 to y equals 1, y plus square root 2 minus y dy, plus, but this other integral that goes from y equals 1 to y equals 2, we can simplify this and it becomes 2 times the square root 2 minus y times dy. And that should give us 9 over 2 as an answer. If we want to integrate this by hand, we would have to do a u substitution to integrate the square root of 2 minus y. The derivative of the inside function is negative 1, so we need to adjust for that. I'm going to go ahead and do this one on the calculator, partly because I'm out of room, and partly because I just don't want to integrate the square root of 2 minus y. So let's do math 9, and we're going from negative 2 to 1. Now, in the calculator, I'm going to use my X button to represent y. So really, I'm just calling my y by the name X, but as long as I do that to all of my y's, and there are no x's in this problem to confuse the difference between x and y, it'll still work out just fine. So first integral goes from negative 2 to 1, and we're integrating y plus the square root of 2 minus y with respect to y. So all the y's actually I typed in as x's. So we've got that. Plus, and math 9 again for my next integral. This one is going from 1 to 2. And we're integrating 2 times the square root of 2 minus y with respect to y. And we get 4.5. Now we see that it's not exactly displaying as 4.5. It's 4.500000421. That's just round off error in the calculator. Because the calculator isn't evaluating these integrals by hand, obviously. It's got an algorithm that it's using, and so it's off by a little bit. It really should exactly be 4.5. Okay, that's a relief that we got the right answer, because that was a bit of a nightmare. And again, this is not a problem where you would be asked to evaluate it using a horizontal cross-section. 24, find the area of the region bounded by y equals square root of x and y equals x minus 2. So our top function here is y equals square root of x, and our bottom function, y equals x minus 2. If we use a vertical cross-section, then this is a dx problem, and we integrate from x equals 0 to this point of intersection over here, which is 4 comma 2. And we can verify that by substituting 4 in for x and 2 in for y in both equations and verifying that it makes the equations true. So our setup, we're going to integrate. This is a dx problem, so we go from x equals 0, and then we go across to the right until we hit x equals 4. We do top minus bottom, so square root of x minus x minus 2 times dx, which is the integral from 0 to 4, square root of x minus x plus 2 times dx. And so square root of x integrates to x to the 3/2 times 2/3, and then minus x squared over 2 plus 2x from 0 to 4. So subbing in 4, we get 2/3 times 2 cubed. 2 cubed is 8 times 2 is 16 over 3 minus 16 over 2 plus 2 times 4. And then when we sub in 0, we just get 0. So this is 16 over 3. if we do the same problem using a horizontal cross-section, we have to use two integrals because down here, right minus left is different than it is up here. So whenever your right minus left changes, you have to use a separate integral. Where does that change happen? Right here on the x-axis. It's where that changes. So these are both horizontal rectangles. So this is dy. We need our y coordinates. So we're going from -2 to 0 and then from 0 to +2. This point of intersection, remember, is 4, 2. So we have an integral from y equals -2 up to y equals 0, right minus left. And I haven't labeled my equations yet. Let's do that. On the right, we know from before this is y equals x minus 2, but in a dy problem, we solve our equations for x. So x equals y plus 2. And then this equation over here was y equals square root of x. So we have x equals y squared. Okay, so now we need right minus left. For this rectangle down here, the right side of the rectangle is touching y plus 2. Minus the left side is touching x equals 0, just 0. So subtracting 0, if we're doing right minus left, it's y plus 2 minus 0. But I don't have to write minus 0. Times dy. Plus, and then my next integral starts at y equals 0 and goes up to y equals 2. Right minus left, so the right is y plus 2. The left is y squared. Times dy. And then we integrate, so I get y squared over 2 plus 2y from -2 to 0, plus, and then my other integral is going to be y squared over 2 plus 2y minus y cubed over 3, and that one goes from 0 to 2. So, and when we sub in 0 here, we get 0, minus, when we sub in -2, we get 4 over 2 minus 4. Okay, plus we sub in the top values, so when I sub in 2 over here, I get 4 over 2 is 2, plus 4, minus 8 over 3, and then minus sub in the 0, but that's just going to give us 0. So let's see here. We've got, if I distribute this negative, we've got -2 plus 4 is just 2. Plus 2 is, I lost my place already. -2 plus 4 is 2. Plus 2 is 4. Plus 4 is 8. So I have 8 minus 8/3. And if we make that all out of 3, that's 24 minus 8/3, which is 16/3. Find the area of the region bounded by y equals x squared and y equals -4x. Y equals x squared is the yellow function. Y equals x squared. Y equals -4x is my blue function. And points of intersection here are going to be -4, 16. We can check that in both equations and make sure it works. And then 0, 0 on the other side. So vertical cross section, draw my vertical rectangle. So this one is a dx problem. My integral goes from x equals -4 to x equals 0. Top minus bottom is -4x minus x squared times dx. Then we integrate using our power rule. So -4 times x squared over 2 is -2x squared minus x cubed over 3. Going from -4 to 0. When I sub in the 0, I get 0. Minus, and then I sub in -4. -4 squared is 16 times -2 is -32. Minus -4 cubed is -64, so I have a double next negative, so 64 over 3. And we can distribute this negative here. So really I have, and let's make everything out of 3. So 32 times 3 is 96. So I have a positive 96 and then minus a 64. And that's going to give me 32 over 3. If we try this one using a horizontal cross-section, then this becomes a dy problem. Points of intersection are the same, -4, 16, and then 0, 0. And now we have to solve our equations for x. So where we had y equals x squared, now we have x equals, and it's plus or minus square root of y, but this is the left side of the parabola. So it's negative square root y. And then the equation on the right, we solve that for x. And instead of y equals -4x, we get x equals -1/4 y. -1/4 y. Okay, that should be all we need. So now we have our integral. This is a dy problem. We're going from y equals 0 up to y equals 16. Right minus left. So -1/4 y minus negative square root y times dy. Then we integrate. So y squared over 2 times the -1/4 is -1/8 y squared, plus, this is y to the 1/2, so then we get y to the 3/2 times 2/3, and we are evaluating from 0 to 16. When y is 0, we just get 0, so we can kind of just ignore that 0, but we have to sub in the 16. So 16 squared, I don't know what that is, but I know 16 squared is the same as 8 times 2 times 16, and the 8's cancel, so really just 2 times 16 times -1 is -32. Plus, okay, so this one's a little trickier. The 2 in the denominator here means take the square root of the 16, which gives me 4, and then cube it, which gives me 64, and then multiply it by 2, which gives me 128, and then divide it by 3. Okay, and then a common denominator of 3 would be -96 plus 128, and that is going to be 32 over 3, which does match what we got when we set it up the other way. (26) Find the area of the region bounded by x equals 1/2 y squared and y equals -1/2 x plus 3. Vertical cross sections. So this is another one where this is just a bad idea. Bad idea to try this using a vertical cross section because we have to use 2 integrals, which that by itself isn't really a big deal. But over here, when we try and do top minus bottom, it's the same function on the top and the bottom. So we end up having to solve this equation for y. This is the x equals 1/2 y squared. We solve it for y, we get plus on the top half, we get negative on the bottom half, and then we finagle our way through that. We're just not going to do that. I already showed you one where I did work it out just to kind of prove that you can do it. It's just unnecessarily complicated. So we're just not going to do that. Horizontal cross section, so much easier. Draw your horizontal reference rectangle anywhere you like in that region, and it's always the same function on touching the right side of the rectangle, the same function touching the left side of the rectangle. So we're going to set this up as dy. Our points of intersection are, I can't tell just by looking on this one. Is it 18? Is it 17? Somewhere in there. The other one looks like it's 2, 2. That's easy to check. So when x is 2 and y is 2, then those are equal. In the other equation, when y is 2 and x is 2, so we're trying to see if they're equal, -1/2 times 2 plus 3 is in fact 2, so that works as well. Okay, so this one is definitely 2, 2. And then I need to find this point of intersection down here. So I'm just going to guess that it's 18, -6. That's what it kind of looks like, the nice whole numbers. So when x is 18 And what did I say? Y is negative 6. 1/2 times 36 is 18, so that works. In the other equation, y, I said negative 6, is that equal to negative 1/2 times 18 plus 3? So negative 9 plus 3 is negative 6. That works. So this is, in fact, even though it's hard to tell just by looking, 18 comma negative 6. Okay, then we want to label our functions. So the blue one on the right is going to be the linear one. That's y equals negative 1/2 x plus 3. We need to solve that for x. So if y equals negative 1/2 x plus 3, then y minus 3 equals negative 1/2 x. And if I multiply everything by negative 2, negative 2y plus 6 equals x. So x equals 6 minus 2y. And then the yellow function, that's my x equals 1/2 y squared. And that one already is solved for x. Okay, so we're good to go there. X equals 1/2 y squared. Our integral, this is a dy now, so we're going from y equals negative 6 up to y equals 2. Right minus left, 6 minus 2y minus 1/2 y squared times dy. And when we integrate that, we get 6y minus y squared minus 1/2 y cubed over 3. And then we evaluate from negative 6 to 2. So when I sub in the 2, I'm going to need some room here. When I sub in the 2, I get 12 minus 4 minus 8 over 6 is 4 over 3. When I sub in negative 6, we get negative 36 minus 36 minus 1 over 6 times 6 times 6 times 6 is minus 36. Wait, let me check my signs on that again, because it's negative 6. Okay, so the negative 6 and the negative 1/6 cancel out, and then I still have 2 more negative 6's, so that's going to be plus 36. Okay, so that's 0. And then I've got here 12 minus 4 is 8 plus 36. 8 plus 36 is 44. So 44 minus 4/3. That's minus 1 1/3. So 42 2/3. Or we can make it all out of 3 and say 44 times 3 is 120 and 12, 132 minus 4 equals 128 over 3. If for all real numbers x, f of x equals g of x plus 5, then for any interval from a to b, find the area of the region between the graphs of f and g. If f is g plus 5, f is always 5 more than g. That means f of x is the top function and g of x is the bottom function. So over any interval, that's going to be true. And if your top minus bottom is the same over the entire interval, then you can set up your integral as a dx problem. So we would integrate from x equals a to x equals b, our top function, which is f of x, minus our bottom function, which is g of x, with respect to x. And we know that f of x equals g of x plus 5. So now this becomes the integral from a to b. I'm going to substitute g plus 5 in for f. So g of x plus 5 minus g of x times dx. And then g of x plus 5 minus g of x is just 5. So now we have the integral of 5 times dx from a to b. If we integrate that, we get 5x from a to b. We sub in the top value, so we get 5b minus, then sub in the bottom value, we get 5a. So 5 times b minus 5 times a. 28. If the area enclosed by y equals 1 over x and the x-axis from x equals 2 to x equals k is equal to ln 4, find the value of k. Okay, we're not given a graph here, but we can find it. The graph of y equals 1 over x looks something like this in quadrant 1. And so we want the area enclosed by this function and the x-axis from 2, which is over here somewhere, to k. So we'll put k just over here. That area of that region, so here's our region right here, this one in here, is equal to ln 4. Well, let's set up our area equation. We can use a vertical cross-section. So this is a dx problem. Our integral goes from x equals 2 to x equals k, top minus bottom. This is y equals 1 over x. The bottom is just y equals 0. So 1 over x minus 0 times dx. And the integral of 1 over x is ln absolute value x. We're evaluating that from 2 to k. We sub in the top value, so ln absolute value of k minus ln absolute value of 2. The absolute value of 2 is just 2, so we can write it like so. And then we can use our properties of logs. When you're subtracting two logs with the same base, you can condense them into a single log where you're dividing. So now this is k, absolute value, over 2. And we know that that is equal to the natural log of 4. So now we have absolute value of k over 2 equals 4, which means the absolute value of k is equal to 8, which means k is equal to plus or minus 8. Now in our picture, we put k to the right of 2, since it told us to go from 2 to k. I guess we're making the assumption that k is larger than 2, in which case we would say k is 8. Number 29, the region bounded by the x-axis and the part of the graph of y equals cosine x between 0 and pi over 2. So let's sketch that out. So the x-axis and then cosine x. So cosine x starts out like this, and this first x-intercept here is the pi over 2. So the region bounded by the x-axis and the part of the graph of y equals cosine x between x equals 0 and x equals pi over 2 is divided into two regions by the line x equals c. If the area of the region from 0 to c is equal to the area of the region for c to pi over 2, find c. So c divides this region into two equal areas. So I'm just going to say that it's right about there. And we're trying to find the value of c. So I think there's a couple ways we could approach this, but we know that our top function here is y equals cosine x. And we can set up an integral to find the area from 0 to c, and then the integral from c to pi over 2 and set them equal to each other. So we might do that. Or we could just find the area of the whole thing and divide it by 2. No, that's not going to work. That's not going to tell us what c is. It's just going to tell us what half of the answer is. Okay, so let's go. This is dx problem because I have vertical cross sections and my bounds are going to be from 0 to c and then from c to pi over 2. So I have an integral from x equals 0 to x equals c, top minus bottom, so cosine x minus 0 times dx. And that, we want to know, where is that equal to the integral from x equals c to x equals pi over 2 of the same thing, cosine x times dx. So the antiderivative for cosine x is sine x, and we're evaluating sine x from 0 to c, setting that equal to sine x from c to pi over 2. So sine of c minus sine of 0 is 0, equals sine of pi over 2 minus sine of c. Okay, so sine of 0 is 0. I can lose that. I can add the sine of c to both sides, and I end up with 2 times the sine of c equals the sine of pi over 2. The sine of pi over 2 is 1. So now I have the sine of c equals 1/2. And c has to be between 0 and pi over 2 based on our picture. So where is sine equal to 1/2? In quadrant 1. 0 to pi over 2 is quadrant 1. So well, sine is equal to 1/2 at 30 degrees, or pi over 6. So c equals pi over 6. And number 30, find the area of the region in the first quadrant enclosed by the y-axis and the graphs of y equals 3 cosine x and y equals x. So this is a calculator active one. Let's go ahead and see how we would do these on the calculator. First thing we want to do is figure out what the graph looks like. So I'm going to enter 3 cosine x. Make sure you're in radian mode, and then just y equals x. And that's not a great window. We're going to go from 0 to, well, let's try 0 to pi. Okay, better, but now I got to adjust my y's. So y's, let's go -2 to 2. See how that does. Okay, that might be all we need. It says the area of the region in the first quadrant enclosed by the y-axis. Nope, because we need this area over here. The y-axis, the graph of 3 cosine x, which is the blue one, and then y equals x, which is the red one. So I need to make my y max higher. And my y min doesn't have to be that low. All right, there we go. So we'll sketch that over here. There's y equals x, and then I've got my cosine graph coming down here. So I'm going to need this point of intersection, and I'm going to do this one as a dx problem. So I just need the x coordinate of that point of intersection. Over here it's 0. And we'll do second calc, intersect, enter, enter, enter. And the x coordinate right here is 1.170. I'm not going to need the y coordinate since I'm only doing this one as a dx problem. And I'll label my graph. This is y equals 3 cosine x. And then this one down here, y equals x. So we have a dx problem. My x bounds go from x equals 0 over to x equals 1.17. And we're integrating top minus bottom. So 3 cosine x minus x times dx. And since this one is calculator active, we'll go ahead and integrate using Math 9. Math 9, I forgot which function I put. Let's take a peek. So this is my y1. We'll come back over here. y1 equals the 3 cosine x, and y2 equals the x. Okay, so our integral goes from 0 to 1.17. 3 cosine x was my y1, minus, and then x is my y2. It's faster to type x, but for the sake of demonstration, I'll use y2 with respect to x, and we get 2.078.